So let us review our normal distribution study through STATKEY, a free software that you can use in this course. So a normal distribution is the bell-shaped curve, and what you see here is a histogram of a data that was randomly drawn from a normal distribution with mean 69 and standard deviation 5. And how do you write it? You write it as normal with parameter 69, 5. So this part goes for the mean, and this typically goes for the standard deviation. And then we had this special normal distribution called the standard normal distribution, whose mean is how much? Whose mean is 0 units, and the standard deviation is it is simply 1 unit, right? So this is a special normal distribution, and again you can write the standard normal distribution as this: mean is 0, standard deviation is 1, and the notation for standard normal distribution is z. So we use z. Remember, the way you standardize the values. Okay, all right, x minus mean over the standard deviation. So for a normal distribution, z will follow this curve. Okay, now we are going to do our normal curve area calculations by using this web-based free software called STATKEY. And a way to obtain that is, one way is just go to STATKEY, and this is the STATKEY software. And now what you have is all these options. So we are looking at normal distributions. So just click on normal, and it shows you that it is showing you the normal distribution with mean 0 and standard deviation how much? 1. That's what it shows you up here. Okay, and you can edit the parameters to enter different mean and different standard deviation the way we are going to do now. Okay, now before we go to the other normal distributions, let's just do some calculations regarding this standard normal distribution using STATKEY. So let's just click on this two-tail. So what it shows us is this, that 95% of the area, or 0.95 of the area, is between z equals negative 1.962, z equals 1.96, or 95% of these values are between z equals negative 1.96 and negative 1.96 and positive 1.96, and that's where your 68, 95, 99.7 rule came from. That actually more precise value is 1.96 instead of 2, as you saw it there. And here you can change it if you would like. Okay, for instance, if I change it to, instead of 1.96, if I change it to 1, what it shows me is this, that 68, here it says 0.683, so 68.3%, which we took at 68%, okay, of the area is between z equals negative 1 and z equals positive 1. And if you go to 3 standard deviations around, let's go ahead and change it to 3 here. Okay, so I'm just typing in 3 here. One moment. Okay, 3. So it shows us 0.997. That is, in other words, 99.7% of the values are between z equals negative 3 and z equals positive 3. And if you want, you can obtain values in between any two. For instance, if somebody asks you to give the values between, say, z equals negative 1.28, I just took a number, okay, to z equals 1.28. All that you have to do is just come up here and just change it to 1.28, okay, and then you can see that 0.799, okay, or about 79.9% of the area, okay, is between these two values, and they will just change to those many standard deviations once you go towards general normal distributions. All right. So now I'm going to recall an example that I did that I showed you using TI-84, that the number of drops from a medication bottle show a normal distribution with a mean of 65 drops and a standard deviation of 2.4 drops. That is, it is a normal distribution with with which parameters? These parameters, okay? And you have to find out the percentage of bottles that will have less than 62 drops according to the nature of this drop. Drops themselves have variability, but let's not go into that detail. So let's see that how would we use a stat key for this. So here we are back to stat key, and it shows standard normal, and what we would like normal distribution with mean 65 drops and a standard deviation 2.4 drops. So what we would do is we will change these edit parameters. That's what we would say. And then the first one says that what do you want the mean to be? I want it to be 65 drops is our unit here. So it just changes it to this format. And now what we would like to do is that we would like to see that what percentage of the bottles are below this value of 62 drops. So what I want to do here is I want to calculate the left tail here, the tail to the left of this. So I'll click on the left tail, and here it's giving me this value here. I can change it to the value that I need. And what was that? That was 62. So when I enter it, it tells me that the proportion of the values below 62 is how much? It is 0.106. Okay, so that's 0.106, which as a percentage, is how much? 10.6%. Okay. And, in the same way, say, for instance, somebody wants me to answer this question, that what percentage of bottles have values between, say, 64 drops and 68 drops. All right. Okay. So first, let me erase this portion here. Okay, and then what we will do is this, that is, now we are going to look for these values 64 and 68. Now you can see in the two-tailed, remember, it just gives us the same value on the left and right. So we may do this, since we want the area between 64 and 68. Let's do this here. That is, let's ask it for the area left of 64. So what it tells me, that it is 0.338. So to the left of 64 is 0.338. And then we can ask it for the area for the right of how much? 68. Okay, so let me print 68 here. So I put enter here, and what it shows me is this here, that 0.106 is to the right, and now it also gives us the area in between here, these two, that is 0.556. So what we have is that 55.6% of the values, one moment, 55.6% of the values are between these two, that is 64 drops and 68 drops. Okay, and again, about this 0.106 indicates that 10.6% will be above how many? 68 drops. All right, now we are going to use it to find the percentiles. Okay, but before that, let's just go ahead and uh, clean up our slate. Okay, so here it's all gone. Okay, so say for instance we would like to find, just say, the first quartile of this distribution, the same distribution which was normal with mean 65 and standard deviation 2.4. So we have to find the first quartile, which is the 25th percentile, right? And then 25th percentile means what? 25% of the area is to the left of this value Q1. Okay, so that means area to the left of Q1 is 0.25. So we are going to the left now. All right, so let's look for the left tail. It just takes up a value and goes to that. It took the last value, I think. So let's just change this value here, the area value, remember, 2.25, and let's just say, let's just enter it. So what do we notice is this, that we have, this is 0.25, that, all right, and the x value here is how much? If you read it, it is 63.381. Okay, so that is the 25th percentile is how much? 63.381, or a quarter of the bottles will have contents of less than 63.381. And we are not distinguishing between less than and less than or equal to in a continuous case. All right, okay. And then now let us go and further review the distribution of sample means. That is, if we draw simple random samples of size n from a population with mean mu and standard deviation, how much? Sigma. Then if we look at the distribution of sample means, which we denote by x bar, then they will have the same mean, but the distribution of averages will be more consistent towards the mean, that is lower standard deviation. So as an example, let's look at those distribution of glaucoma medication bottles where we had mean as 65 drops and standard deviation as 2.4 drops. And we saw in our calculations that over 10% of the bottles have a mean of lower than 62 drops, which may run a patient out of medication during a given month. So what generally is done for such cases is this, that they give the patient a set of a set of 4 bottles. Okay, so that what will happen is this, that is, if you look at the total of the 4 bottles, or in other words the averages for that, then it would be unlikely that the average will be more unlikely than 10% that the average will be less than 62 drops. Okay, so in other words, what we are looking at is this, that we have one moment, let me choose my tools here. Okay, so what we have here is, so now this is, so here we got mu equals 65 and standard deviation equals 2.4, and here somebody is getting a random sample of size 4, okay, or a random sample of 4 bottles. So in this case, if we look at x bar, all right, the sample mean of simple random samples of size 4, okay, then they will have a mean of still 65, but the standard deviation would be lower. That is, sigma is 2.4. So 2.4 over square root of 4 would be how much? 1.2. So let's go ahead and calculate that what percentage of samples of 4 bottles will have a mean of less than 62 drops using the stat key. Now, notice that here we are using the property that X, that is the contents of the individual bottles, have normal distribution. That is, the population has normal distribution. So when the population has normal distribution, the sample means will also have a normal distribution. And in this case, the parameters are what? 65 and 1.2. And I didn't change the parameters there. Let me just change it. Here the mean is the same, that is 65, but the standard deviation is how much? Edit parameters. I didn't do that. Okay, so 65 and that. So now the distribution has become different, and you can see the tail to the left of 62 has shrunk. So what we want to know now is that we want to know the samples, okay, or rather percentage of samples with mean X bar lower than how many? 62 drops. So what we will do is that we will just go to the left tail, which is right here, and change this value to how much? 62. I'm typing 62 in here. So we got, so if you look at it, we got 62 here. Okay. And this percentage is how much? 0.006. Sorry, this proportion is 0.0062. That is only 0.62%, which is a good coincidence, okay, of the samples of size 4 will have contents less than 62 drops. All right, now let's finish with the review of just one more idea. So say we have a question like this, and I'm taking the same question that I did for the TI-84 example, that a computer manufacturer has determined that the mean time that it takes for for a technical trouble to resolve over the phone is 16.7 minutes, okay, and the standard deviation is how much? 10.2 minutes, okay. And they have this, they want to see that how do the averages of simple random samples of size 100 vary. All right, so remember this, that we had what you called central limit theorem, and in which for this course we assumed that if the sample size is 30 or larger, then what will happen is, doesn't matter whether the population has a normal distribution or any kind of distribution, the sample means, that is the X bars, will have approximately a normal distribution. So let's just go to, and here what we want to know is, we want to know the probability that X bar will be more than 20. All right, so let's just go to the stat key. So here we have this situation, and what we are using is this, that our sample size here is larger than or equal to 30. So we can apply the central limit theorem for X bar, but just for curiosity's sake, let's see if this distribution can be normal or not. So what I'm going to do is that I'm going to enter this value of mean in here, which is 16.7, and the standard deviation is 10.2. So you can see, if you look at 0 here, or let's just look for the left tail for 0. Okay, so it gives us an unrealistic situation, that is about 5 percent of the calls will take less than how many? 0 minutes if the distribution is normal, and that's not possible. So in this case, we know the population does not have a normal distribution, but since the sample size is larger than 30, uh, we can take, or we can assume that X bar, or the sample mean, has approximately a normal distribution. Okay. All right. So let me erase this writing here. Okay. And then we will go for the part that we are curious about. Okay. So we have, so we will erase, let's just erase this also, and look for how the distribution of X bar will look like. So for X bar, we will have a normal distribution because of the central limit theorem. The mean would be the same, but standard deviation would be how much? 10.2 divided by square root of 100, or in other words, that will be a normal distribution with mean as 16.7 and 10.2 over 10 would be how much? 1.02. So now we will change the parameters again. So let's edit the parameters. So here we got 16.7 remains the same, but this goes down by 10. So when we do that, you can see that let's go for the right tail. Okay. And for the right tail, which value do we want here? We want the value 20. Okay. So here is 20, and it tells us that 0.00061 is the proportion. So here it is printing that as 0.00061 is the proportion that will be higher than 20 minutes, or 0.061% of the calls will last for more than 20 minutes. And actually, for probability, our answer should be this, because I remember that's what we were investigating. So let me know if this doesn't make sense, and if you have any further questions on this. All right.